Okay, so we continue our study on laminar boundary layer. And yesterday we talked, I think previously in start in chapter 4, we already looked into the von Karman. Okay, so and then we have another solution called Blasius. Okay, and then so this is everything is actually for laminar. Okay, and then yesterday also we introduced to one equation called Faulkner-Skan. Okay, so and this is used for the wedges here. So you have wedge here or the boundary layer that occur not parallel with the upcoming free stream velocity. So according to the velocity that comes at the front here. So and then we will see the usage of Faulkner-Skan later on. So this is just to introduce you with a few equation. And then today I would like to introduce you another equation called Twits. Okay, so we have a Faulkner-Skan and another, we have a Twits equation. Okay, so it might be quite it means that we have a lot of equation and so on and so forth. I think for this stage at this moment, just please see all these equation first. Later on, we will summarize the usage or the what actually the way we handle with these all equations. Okay, and today for the tweets here. Okay, before that we need to know about the pressure gradient first, and then the effect of the pressure that occur when pressure occur inside that boundary layer. Okay, so I will update my notes in my website from time to time. So please please open my website time to time. Okay, so we have here. Okay, analysis for laminar boundary layer on thin plate. Okay, can be conducted using von Karman and also Blasius solution. However, you must know that Blasius solution is only for laminar, but von Karman here can be used for both laminar and turbulent situation. So in the first place, okay, in the first discussion of laminar boundary layer, so we will use thin flat plate. And we assume that there are no pressure gradient in the boundary layer. So I will show you later on. But the idea is in thin flat plate, there are no pressure gradient. So because of that, okay, there are no separation occur. So this is the keyword. So because there are no pressure difference, or the no pressure gradient means if there are pressure, so the pressure is still constant. The pressure will be in constant value. So the pressure gradient means pressure keep changing. So and then what is separation? Separation, or to be specific in this chapter, is the boundary separation. Boundary layer separation is the detachment of a boundary layer from a surface into a wake. So mean it start to have, you have a turbulent, a very rough turbulent, or a circulation, a vortex at behind your object. Okay, so why that happen? Because the boundary layer is actually goes out, not occur on the surface anymore. Okay, so separation occurs in flow that is slowing down with pressure increasing. So this is the condition for the separation to occur. So it's separation occur in flow that is slowing down. So and then when the velocity is decrease, so the pressure will increase. So this is the idea of Bernoulli equation. And after passing the thickest part of a streamline or passing through a widening passage, okay, so it is So why the pressure why pressure can be changed, okay, why pressure can be fluctuate, because the surface sometime will trigger this phenomenon. Okay, so and then flow separation occurs when there is a change of velocity and pressure. So because pressure different is occur, so the flow separation can be occurs. So another again I write here that is the reason why there are no flow separation occurs on the thin plate. Okay, so this is the one of the example of the separation, the common one, occur on the cylinder surface. It is no separation on the thin flat plate. Okay, so let's say we have a cylinder here. So, and then we found that the flow will flow up here. Okay, I changed the color to red. Okay, it's flow around the cylinder here, and as we learn in ideal flow, so because we learn uh, how to draw the streamline for the flow around cylinder. So we have the stagnation here because the flow will hit the surface here, and then it stop for a while. That's why in stagnation condition, stagnation point, the velocity is zero. Okay, please remember about the ideal flow. And then the velocity, the flow will go around the cylinder, and then until this one, another stagnation point occur. Why? Because it collide with another molecule from the bottom here. It stop for a while, and then it goes like this. So this is for ideal condition. So what is ideal condition? Means a situation where the viscous effect is not included, is not account. So mean the viscous effect mean the viscosity actually not give us resistance. So means there are no, the viscosity is there. In our calculation, we will put the density, we will put the kinematic viscosity and so on and so forth. But the effect of that one is not appear. So mean that there are no shear stress. Mean there are no slip condition that occur on the surface here. Means that there are no velocity distribution occur on this cylinder's surface. Okay, that is the ideal condition. Means the simulation one, a very perfect flow around a cylinder. But in reality, we found that might be in very slow and a very slow flow. So we could get flow around the cylinder, very nice one. So we have here, and then it goes around the cylinder, and then might be they will have something like this. So they're very smooth. Okay, and then but if the velocity start to increase and so on and so forth, so might be you will find that the flow actually will go like this one. So it will detach here. So it will detach here until it will create some kind of empty space here. That's why we will get a wick. A wick means, it cannot be a vacuum in this area. So what happened is, so they will the a few molecule here, so it will suck, because if this is a vacuum. So if this is a vacuum, so mean the flow will comes here and will create a turbulent or wake or any a very unpredictable motion. So this is the wake, the separation. So now we will discuss about the wake later on. So but first we are now discussing about the separation. So separation here means a point where molecule of a boundary layer here detached from the surface. So I hope you could explain the phenomenon of separation. So and then why that happened? So it's explained that because there are increment of pressure. So, okay, please refer back to our calculation on flow around cylinder that we discussed in chapter 1 to 3. Okay, in chapter of ideal flow, you know you have doublet plus linear, and then we will have stream function of a flow around cylinder. So this is the example of flow around cylinder. So we have a free stream velocity here. So we have a free velocity, okay, we have a free stream velocity here. So, and then the velocity will go out there. Okay, so I think you could say that at this situation, at this point, the velocity will become the highest one. So when the velocity is the highest one, so means the pressure will become the lowest one. So, and then when the velocity is start to reduce, okay, until it will flow at equal to the free stream velocity at this line, at this area, so means that the pressure is start to increase back. Okay, so this is the idea when the flow changes on the curved surface. Okay, so and then what this happened? Okay, so it is happened because if you see here, so this is the velocity distribution. So the velocity distribution here means we have a velocity. Wait a minute. So we have a velocity distribution here. So according to the previous, according to this graph, so we found that at this point, so at this point, the velocity is in maximum. So, and then the velocity start to reduce, mean the pressure is start to increase. So what happened to this velocity distribution? So we found that the pressure here will become higher and higher, bigger and bigger. So it seems that the pressure here will become, it's changed from negative to positive. So it's become bigger and bigger. So it has tendency when the pressure is become big, high pressure. So it will push this layer detach from the surface of cylinder. So that is the actual the simplest explanation of separation on cylinder surface. So this is only occur at on the curved surface. So on this surface, on any curved surface. So that's why in aerofoil, for example, so you will have the separation and so on and so forth. But if your your object is thin plate here like this, so there are no separation will be occur. So and then in terms here, so we have a backflow. So a backflow here means the flow here, okay, will, because it start here, so and then when it start to detach, so and then the flow will comes in and create wake. Okay, so I hope you could find or at least study about the formation of a boundary layer, as well as the formation the formation of the separation of the boundary layer. So this is in this note, so I explain about the pressure at this point. So for example, normally in ideal flow, the dpdx is actually negative, okay, but at certain situation, okay, so the pressure is start to become zero. So and then the pressure is will increase, and then at one moment, okay, so we found that the separation will be occur. So and then when the pressure becomes greater, so they will create a backflow here. Okay, so this is the explanation. So I hope you could read this letter. Okay, and another thing that have phenomenon of detach is when you go for a nozzle. So for example, we have a nozzle here. So, and this is actually occur in compressible flow. So when you have an engine jet and so on, so and you compress air inside a convergent and divergent nozzle. So I think you still remember about the convergent and divergent nozzle, and then the air is come in here. So and then it compress, so it has velocity, and then it will release at high velocity. So at certain point, okay, at certain point, the air will detach from the surface. So it will become like this. So and then here, so we have a backflow. So and then I have a picture of that. So it's okay. So means that I hope you could understand about the separation, and the phenomenon means that the physical phenomenon that's occur is the wake. So in at the end of this chapter, okay, at the end of this slides, I will show you a few pictures about wake, or you could search by yourself. So it's quite an interesting phenomenon of this one. So and then to start to calculate the separation point here, so we introduce you the correlation method of Twitch. Okay, so Twitch is actually used for we read here. So von Karman solution can be used for laminar and turbulent boundary layers. However, Blasius solution it's only can be used for laminar boundary layer. And von Karman and Blasius used for flat plate problem or situation that does not have pressure gradient. So mean the separation will not occur. However, for any curved surface, okay, whether it is a sphere or a circular surface or a aerofoil and so on, there is a pressure gradient. Okay, so and then the flow separation have probability to occur. So in this case, okay, we need to use Twitch equation to be used. And then the one of the usage of a Twitch equation is actually it could predict the separation point. Okay, so and then here I will show just give you the equation. So the von Karman integral methods it's come from here. So I think you already know this because we have an exercise about this. So we have tau rho u square d theta dx, and then it's also related with CD 1 over 2 rho u square. So and Twitch equation can be written as this one. So this equation is actually is come from curve fitting from experimental works. So means it is not easy to derived by mathematics because the idea is each if you read the textbook in our viscous flow, you read the whole chapter 4, so you will find that Blasius is doing in terms of, let's say it's do from the Navier-Stokes equation, and then it's do the experimental work. Okay, so and then from the experimental work, so you get a lot of data, and then Twitch and also Scan and also Blasius, they will do the curve fitting. So means that from all the data, for example, you will get a lot of data here. For example, you have a lot of data, and then what they do is they, for example, they assume that this correlation is in straight line. So they draw a very good straight line, and then they will write an equation from this straight line. So this is what actually happened in Twitch and also Scan. So that's why we skip that one. If you read, I think you could understand the method of Twitch. So finally, Twitch proposed that the tau over rho u square is equal to CD times 1 over 2, and then it is can be can be write as d theta over dx plus 2 plus h theta over u du dx, which is the theta here is the momentum thickness, and then the h here is actually the shape factor. So the shape factor is actually when delta star, the displacement boundary layer, and also the momentum thickness, the ratio of delta star and theta is dh. So, and then we have negative du over dx is equal to positive dp dx. So I think this is, you know, this is actually not from, if you read more about this one, so you will find that this correlation is actually depends on the graph. The graph that I show you about the flow around cylinder. So means that when the difference of velocity, mean the du dx, it will give reverse action of pressure. So mean the negative, the increment of velocity means will create the decrement of velocity here will give the increment of pressure. So the relation is actually come from that one. Okay. So and then the higher the value of h here, so the stronger the adverse gradient. So adverse gradients means the pressure is become bigger and bigger. So and then the separation could occur. So for laminar flow, so if the h is almost equal 3.5, so we can say that on that point, so the separation will occur. And for the turbulent, so when h is almost 2.4, so the separation will be occur. So we still in a laminar condition, and later on in chapter 5 and 6, so we will go to evaluate the turbulent flow later on. So this is actually what we did. Okay, this is actually the curve fitting from the experiment data. So we found that if we plot the y over delta, means the y distance, the height and the height of delta here, and also the u over u here, the velocity distribution. So, and then we curve for different delta star over delta. So this is actually proposed by the Thwaites and Blasius, because if you read from the textbook, you will find that Thwaites is actually modified the Blasius equation. So it's the most common explanation is actually is start to add certain parameter in f double prime plus f triple prime, the equation of that one with another equation. So, and then we found that here, so at 3.5, the separation start to occur. So this 3.5 is actually based on the observation. So based on the experiment, so it's found that 3.5, the separation can occur. So, and then if you do in a turbulent flow, so you will find that it is around when it reached 2.4. However, so this value is actually changed when you have certain modification on your surface. For example, your surface is very, very smooth, or your surface is might be a little bit lubricated. So you put a certain, a fluid or lubricant, for example, to make it a real smooth, and then, or you create any resistant, the artificial surface, for example, you put a dimple like a golf ball and so on. Okay, so it will give you different value. So, and then for laminar flow, okay, so for laminar flow, a simple and effective method was developed by Thwaites, who found that equation 1 previously that I show you here. So this is the equation 1. So, and then can be correlated by a single dimensionless momentum thickness variable lambda defined as this one. So it starts with this, means from that, for equation 1, so he plot a graph, and then he did the curve fitting and so on and so forth. Then he found that lambda is actually will give us a certain value. So, and then using a straight line fit to his correlation, Twitch was able to integrate equation 1 in closed form with the result of this one. So, and then this is the equation that he proposed. And finally, he could say that the lambda is equal to minus 0.09. So if lambda here is reach minus 0.09, so at that point, the separation will occur. Okay, so however, in these notes, I will give you two types of Twist equation. One is for the almost plain, almost flat plate. Okay, just now I say separation only occur at curved surface. Yes, it curved surface. Okay, for example, we have an aerofoil here. Okay, okay, so we have an aerofoil here. Okay, but so the pressure change, the pressure gradient will change because the it has a curved surface on this one. Okay, however, if you see the nature flow on this surface, so it will be a planar surface. So mean it's just a flat surface. So another equation will be given for the twist. Okay, for an object which is totally circular. So, for example, flow in pipe or flow around cylinder, flow around sphere. Okay, what is the difference between flow on the aerofoil like this one? So, as I said, so it will create a boundary like here, the boundary layer like this one. Okay, it start from here and it create boundary. So here, so we have the boundary layer here. Okay, so we have the boundary layer here, and then it's still in 2D dimension. So means we just evaluate the x here, for example, and this is x, and all this will become its y, because normally the changes of z can be neglected. So it's still in 2D or a planar surface. But for a circular like this, okay, a circular like this, okay, it will create a totally it will create boundary layer, but you need to evaluate this one using the idea of axis symmetry plane. No, axis symmetry. We classified that one as axis symmetry flow, because if you cut, means you could imagine that, for example, we have a cylinder here, and then it has a boundary layer on it. So, okay, you have a boundary layer on it, and then you will find that you will cut the cross-sectional area can be anywhere. The cross-sectional area can be cut at any plane, then it will give you totally the same shape of boundary layer. Okay, so means I hope if you cut in x-axis or y-axis or z-axis, it will still will give only a circular shape like this, and the idea of boundary layer like this one. Okay, so it is different from this planar surface, because if you cut it like this one, if you cut at this axis, so you will have aerofoil and also the boundary layer. So if you cut this one, if you cut at this axis, so you will totally get different shape. And then if you cut in y-axis, for example, so it will totally different shape. So this is not axis symmetry flow. So it is actually two different nature of flow actually. So I hope you could study about the axis symmetry flow and also about the formation of separation. Okay. However, this kind of evaluation, so we have von Karman, we have Blasius, and then it's come on the Fafner's Kahn solution. We have Twit solution. Actually, only von Karman solution can be done on just solution on paper. Okay, not only von Karman. So a von Karman solution is the one. It's easy to be tested as a examination question. Another, as I said, start from blast use. It is actually for research of boundary layer. So you need a lot of data. You need to conduct something, and then you need to know, use a numerical solution, whether it is a coding like a MATLAB and so, or a very simple software like Excel. Okay, that's why if you see any textbook, they will talk about von Karman solution and also the introduction of Blasius. Okay, but in our master, I would like to introduce this one. I hope if you do master project for about boundary layer and so on, okay, you could start to enforce the idea of tweet and so on, because this idea is quite accurate, because it starts with the idea of Blasius. As we know, Blasius is an exact solution. So it's modified the Blasius because Blasius is only suitable for laminar on thin flat plate, and then they modify into a wedge, mean when the boundary layers occur not in parallel with the free stream velocity, and also when the boundary layers start to separate from the surface. So, and then this is the relation. So means that it could get only another graph, which is the S here. So it is equal tau over mu u, so which is equal lambda plus 0.09 by the power of 0.62. And this power of 0.62 is actually based on the curve fitting conducted by tweets. So, and then the parameter is related to the skin friction by the identity, so it should become 1 over 2 CD and Rho theta. So what is the Rho theta? So Rho theta is actually the Rho number based on the location of theta. Okay, so it is not based on the distance of certain object. So, and then so finally, if we calculate it, so this can be done in as a mathematical solution. So if we assume that u is constant, and then lambda is equal to 0 and theta is 0, so we could find that theta square is equal 0.45 nu x and u, and finally we could have this one. Okay, we could convert into this one, which is the theta is equal 0.671 over square root Rho number. So it is almost similar with the Blasius solution. Okay, so in Tweed's equation, there are two main equations that you need to understand. First, this is the equation. So, and then this is the value of lambda. So the idea is, first we need to calculate what is the theta square, or the momentum thickness square. So, and then after that, after we get this one, so and then we substitute into this equation, and we need to develop our own graph, because this is not just a single line equation. So based on our graph, okay, so means you need to have ability to draw a graph. Okay, you need to make sure that your lambda here is negative 0.09. Then at that point, you could assume that the separation will be occur.